Kp is our CL alpha, okay? Which is strong function of the aspect ratio, just keep it in mind. That's okay. So the normal force coefficient is simply in the regular operating condition is simply this guy times cosine alpha, correct? It's this component because this is alpha. Okay? This is horizontal, u infinity, and this is alpha. And the suction force is the other component. So C suction is Kp sine alpha, and it's another sine alpha, right? Actually, I should have done it down anyway, so I will do it again. So I have this guy vertical. And this is the normal. Kp sine alpha cosine alpha. And this is the suction force. So this is the usual operating condition. Now the thing is that we don't have suction force anymore, right? We have flow separation from the trailing edge. We have a leading edge vortex. And when you have separation at the leading edge, there is no suction force, of course. The suction force is due to the flow around the leading edge and the infinite suction here, right? So if there is no flow around the leading edge and if the flow separates at the leading edge, you will not get suction force. So if I don't get a suction force, I don't have this. I don't have this thing. And my lift actually will be the component of this guy. So this is what we call, or what Pulhamus called CLP. What's CLP? Is the potential flow lift without leading edge suction. Okay? Can you give me an expression for that? What's CLP? What's CLP? What's CLP from this figure?
Kp sine alpha cos alpha.
Yeah, so it's this guy times cosine alpha, right? So this is Kp sine alpha cosine squared alpha, and you can see this is the 2 pi kind of thing, right? So 2 pi sine alpha is here, and you lose lift by cosine squared. Of course, cosine is less than 1, so you lose much lift here. Okay? So the leading edge suction, and you get drag. So this picture will have drag, right? But we don't care about drag now. The thing is, so what Pulhamus said, okay, so this is the potential flow without leading edge suction. What about the leading edge vortex? We need now the lift, the vortex lift. So this is what I get if there is a flow separation here at the leading edge and there is no vortex lift. But luckily there is vortex lift. How much vortex lift do I get? What Pulhamus said, it was interesting in the following sense. He said, well, you know, so we expect an additional lift due to the vortex, and since there is no suction anymore, all the forces are pressure forces, we expect an additional force here, right? This is CNV. The normal force due to the vortex. This is what we're looking for. We don't know it yet, right? So that now if you want your total lift, this will be my total lift. The blue part is the CL due to vortex, and the red part is the potential flow without leading edge suction, okay? And you add them together. So we're looking for this guy now, and it was very straightforward to say, well, this is related to the suction force in some sense. So he said that this is actually proportional to the suction force. This one was Kp sine squared alpha, right? So he said the CNV is actually another constant times sine squared alpha. So the total lift now, which is CLP, potential flow plus vortex lift, is simply this guy, cosine squared, plus another constant, because we don't know it, it's proportionality, sine squared cosine alpha, right? Where Kp and Kv are strong functions of the aspect ratio. This is what Polhamus did. And it works pretty well up to 20-25 degrees angles of attack, which is of interest to aeronautical engineering back then and even nowadays. It's very famous and useful kind of thing. Any question about Polhamus leading? They call it leading edge suction analogy because it's as if this is what he exactly said. He said that this guy will rotate 90 degrees. I mean, the force doesn't rotate, but to me, I like to say it this way: is that this additional normal force is related in some sense, is proportional to the suction force that has been removed due to the separation of the leading edge. Okay. Any question? So going back here, this is Polhamus in 1966, and this is his illustrative figure. I mean, you can go to the report and see how his theory match experiment. But this is the illustrative figure. This is the potential flow left without leading edge suction, zero suction curve. This is left, and this is angle of attack. No suction. If you have suction, you'll get higher lift, but this is not allowed anymore because we have separation at the leading edge anyway. The vortex lift added this extra, okay? And you can see it from our picture here, our also illustrated picture here. So I have three arrows here, right? We have this guy, this red guy, and I have this blue guy, this black guy, and the blue guy. This is the attached flow kind of thing. If you lose leading edge suction, you're here. But now you're getting more vortex lift. So this is the net. Okay? Okay, one more interesting thing actually is that this leading edge vortex kind of thing was essential for the flight of low aspect ratio and high speed delta wings. Let's see. If you want to design an airplane to fly with high speed, supersonic, what are the most two characteristics that you always find in every single supersonic airplane? Can you tell me?
Sweat.
High sweat, very good. High sweat, that's highly sweat. Highly, 70 degrees, right? Not 35 degrees like conventional airplanes. Why?
Prevent shock. Or delay shock.
Okay,
The wings have to be inside the macro.
okay. That's related. But actually, even for the usual airplanes that we sweep by 35 degrees, this is purely for drag reasons, okay? Why? Because remember this curve, CD versus Mach number. Remember the MDD, the drag divergence Mach number? So beyond certain Mach number, the drag this is MDD, it's for drag divergence. The drag diverges. We have huge drag rise due to compressibility effects. Luckily, the effective Mach number is what really matters in the following sense. If this is your Mach number, what really matters is the one that is perpendicular to the leading edge, which is your Mach cosine, your sweep angle. This is the sweep angle, okay? So if this is, say, 1.5, if you sweep by 70 degrees, you get here like 0.5 or so. This guy is around 0.7 to 0.9, okay? So you sweep high enough to be before the drag divergence. Okay, so we got that, that's fine. What's the other characteristic of a supersonic airplane?
Pointy nose.
What?
Very sharp nose.
Yes, that's right. for the wing? Any other characteristic? Shorter wings. Short span. Right? So actually aspect ratio is small. Why is that? Structure reason now, it's not drag anymore. Because first of all, you don't need the large wing. Why? Because you fly super fast. So you don't need much area, actually. Okay, actually, you don't need much of it, but you just, because you cannot go instantaneously from 0 to, you know, the supersonic, you will fly subsonic and transonic, so you need some area there. So anyway, the issue is if you have very large span wing flying this with this huge load, the supersonic, you will need much stronger structure, so it will penalize your performance. And you don't need it. So typically, every supersonic airplane is low aspect ratio. Okay?
Operator,
Yes.
is the jump in the drag coefficient caused by the shock?
I'm sorry.
Is the jump in
No,
the
this is compressibility effects.
Oh,
Shock will worsen it,
oh.
exacerbate it. So it's to the extent that these two guys are now concomitant. They are associated. They are always associated. People say low aspect ratio, highly swept wings. Okay, they are always, you know, whenever we design a highly swept wing, it's low aspect ratio. The issue is a low aspect ratio. Okay, so this is our design, our supersonic design. Now we have a low aspect ratio. Low aspect ratio leads to what? We just stated what?
Or CL.
Your CL alpha is higher or lower?
Lower.
Lower. You lose your sublift sensitivity. What about the sweep? Higher sweep means what? It's the same actually. Okay? It goes to the first order by cosine the sweep. Multiplied by cosine the sweep. So both leads to lower lift sensitivity in the following sense. If this is your CL versus alpha, and this is your lift curve slope, now it's something like this, okay? Which means if you need high lift coefficient, why do I need high lift coefficient? Why do I need high lift coefficient? Ever. Why? This is wing area, it's fixed. During flight, air density have no control over the weight, it's fixed during flight for first order or whatever. So the issue is, if you want to keep this equality the same, always satisfied, if the velocity decreases, the CL has to increase, right? By the square, to increase it much. This guy increased to half, this will be half to multiply by 4. Increase your CL by 4. And when this guy is at lowest,
Takeoff.
yeah, takeoff and landing, right? So takeoff and landing, we have a problem, so you need higher CL. Okay. So if I need high CL, that's fine. I will be able to attain it with the low aspect ratio, highly swept. But the issue is that I will attain it at much, much higher angle of attack, right? That's okay. What's the problem also? What's the problem? The problem is here. So if you need your airplane to tilt that high on the ground, it will cause tail scrape, right? It cannot do half at certain angle. It will cause tail scrape. This is not very problem. This is not a serious problem if you have a fighter airplane in the sense that the weight is not that high, plus you have a very strong engine. But for a civil airplane, it's detrimental. You have huge weight, much larger than fighter airplane, and you don't have the same luxury when it comes to engine. It's detrimental in the sense that with this picture, the Concorde would not be able to fly. This was a serious problem in the Concorde program. It was about to actually terminate the program. But then they realized if you have highly swept wing, you will have a leading edge vortex. So this is not your total lift. your total lift is something more, right? Your total lift, add to this guy, yes, you have much lower slope than this guy, but add to it the vortex lift, right? Just because of the vortex lift, due to leading edge vortex, Concorde was able to fly. The vortex lift doesn't come for free. It comes with what? With much extra drag, right? Because there is no leading edge suction. The suction gives you more lift, rotates 90 degrees, like Parham said. But you have now drag. So, and it's a huge drag. So actually the Concorde, if you have anybody who heard it operating one time, it's so noisy. It has huge engines. It's so noisy. So I had people near the Heathrow Airport, London. The Concorde used to fly from there all the time. They can tell immediately just by sound if this airplane is the Concorde or not. So this was the story. Okay. What's the conclusion? The conclusion is the leading edge vortex was necessary for low aspect ratio, high strut wings to, just to take off. It was a very serious problem to the Concorde program. Back to flapping flight, because it seems that we spent too much time outside of flapping, but anyway. Back to flapping flight. So insects like the Concorde, they exploit leading edge vortices. And back to flapping flight, Dickinson, in this science paper 1999, which has more than 300 citations actually, he did very simple experiment, Just a tank, oil, and a motor revolves this wing that is similar to an insect wing at a constant speed. That's it. So from here to there at a constant speed, 180 degrees in an hour. That's it. And measures the lift. Okay. So this is what he found. So I'm telling you, it's a constant speed, right? It's a constant speed, so it's steady measurements, okay? But it's rotating in the sense that this rotation will allow the span-wise flow, so you will have a stabilized leading edge vortex. And here you can see here, at the beginning there's some transient. Maybe there is a dynamic slow kind of thing here, but that's okay. After a while, you get a constant lift at each constant angle of attack, a constant lift all over the time, okay, during the excursion. And when you plot the value of this lift versus the value of the corresponding angle of attack, you get the CL alpha curve. And look at that. This is the CL alpha curve, okay? Do you notice anything weird that you didn't see before? Is it a familiar CL alpha curve? This guy? There's no stall. These guys don't stall. Insects don't stall. It's a very smooth variation. The shape that we use